currently, so my Tuesdays, I have more freedom on my Tuesdays now because Virginia, my folks that I'm collaborating with at Virginia Tech have settled on Thursdays for our group meetings and times I need to go down there. So Tuesdays I'm open if you want to send me an email, you want to come meet sometime then, particularly this week when my daughter's out of town and I don't have to take her to gymnastics. So, tomorrow's a great time as well. I'm going to hand back your tests, and you've seen your midterm grades. I'm going to hand them back at the end, so you need to remind me at the end so I just don't keep going. No, I can't keep them. You need to take them and look at them. But if you don't like where your grade is or how the test went in the class, please, I encourage you to come get help. Either go get help from you've got it's no longer the Center for Teaching and Learning, but you can get subject tutoring. Okay, you can get help with subject tutoring. You have my office hours. I'm happy to sit there with you and give you practice problems. And if we need to work backwards so for a certain concept, we need to work out a more basic concept to build up to it. Happy to do that sort of stuff. Okay. That said, for today, for these office hours, people have not been taking advantage of my office hours. If nobody's kind of there or has told me they're going to be there, I'm going to go upstairs and work in lab. I'll put a note on my door. I just have to get stuff ready for biochem. They did construction, blocked off the biology department over break, so I have to make up for that. So anyway, I want to help you guys. Please come get help where you need it. All right, so questions on where we are, what we're doing in the class? Okay. All right, then what we're going to do is we're going to be talking about acids and bases today. And what I want to do before we get really into that is I want to review, we've all had a break here, right? We've forgotten most of what we were doing before break. And so what I want to do is just review equilibrium constants, because we were talking about equilibrium before we went, and we need what we learned about equilibrium to talk about or just discuss acids and bases. So let's take a reaction that looks like this. So we've got water. Water is a liquid. Water can react with hydrochloric acid. That's a strong acid, so it's going to produce mostly, this is what we call hydronium ion. Okay, we put an extra, we take an H plus off of the HCl and we put it on water. And chloride ion. All right, that's an acid-base reaction, actually. And we can model that using an equilibrium constant. So we can write an equilibrium expression for that. When we do that, we write K, big K is our equilibrium constant. And we're going to be using a Ka here. There's a Ka for acids, for the acid reaction. There's also a Kb for base reactions, but it's a big K. It's an equilibrium constant. It's the same thing as before. We just give it a little letter there. So Ka is going to be equal to products over reactants, H3O plus, Cl minus, okay? And then I'm going to have HCl on the bottom. And I don't put the reactant of water on the bottom because water is a liquid, it's super concentrated. We don't put liquids or solids on the bottom or in the equation. For solids, what's going on is we learned about we have certain solubilities for solids. If you have solid in a reaction, the assumption is that if any of it gets used in solution, more dissolves in. And so the solid concentration of what that solid dissolves into is constant. Any of it gets used up, more dissolves in to replace it. So it's like the liquids, but it's not that they're super concentrated necessarily. Questions on what I've done here, because we're going to use this in terms of acids and bases. Okay. Before we go on, I want to talk about a couple different things, terminologies we're going to use. There's three different ways to refer to that H plus. Okay. So we can talk about H plus. We can talk about protons, which is how I usually say it. So I'm going to say protons more than anything else. And H plus is a proton, right? We look at H on the periodic table. Neutral H, how many electrons does it have? One. Okay, we have one proton, we have one electron. If it loses the electron, it becomes H plus. It's just a proton is all that's left. So I say protons more often than not. And then that proton could stick to a water like we see here, and we call that a hydronium ion. Okay? These have different names. These two things are identical. This is somewhat different, but you should just treat these as all the same thing. Okay, in terms of acids, in terms of thinking about it, our model, that's what's going on there. Okay, and I wanted to show you a picture down here before I go on. So then here is a model of what we can think is going on with that H plus in water. We can think about that H plus has a bunch of waters coordinated to it. Okay, or we could think about that H plus as sticking to a water. Both of those models are valid. Both of those models will work. You can use whichever one you like better. They work for what we'll be doing. Yes?
Although, aren't they different because on the right it's a covalent bond and on the left it's intermolecular forces, so isn't it?
They are. So the question is, aren't they different? Yes, they are different in terms of models, but in terms of how you think about acids and the behavior of acids, you can just pick whichever one of these is going on and put it in your head and think about it that way. So both work. If you go on and you do some very specialized work where you're thinking about what's going on with these in water, it would matter. But it's not going to matter from the perspective of this class. And frankly, for my work, it's not really mattered in terms of most of my research. Actually, now I do computational chemistry research, so I bet it matters, although maybe not at the level I do it. Okay, so we introduced this set of terminology, and like I said, I'm going to be saying protons, and when I say protons, I'm going to be writing equations with both of these, and you just need to be able to interchange those in your head. Okay, so then before we move on, we're talking about, I haven't actually defined what an acid is yet. There are a couple different definitions we're going to use today. We're going to use an Arrhenius definition, and we're going to use a Bronston-Lowry definition. And the difference really is whether there's water around. The Arrhenius definition only works, well, it could work with maybe more than water, but mostly only works with water. And the Bronston-Lowry definition works in various solvents that aren't water. So let's just talk about what the Arrhenius definition is. All right, so we have an Arrhenius definition of acids and bases. An acid produces H plus in water. I'm going to say protons. Okay, and a base produces OH minus or hydroxide in water. Okay, so let's go ahead and look at a couple examples of that. So your book likes to do HCl. We'll go ahead and start there. We've got a bunch of acids we're going to look at, but so we have HCl. If I put that into water, it's going to make H plus. Okay. I'm not showing it reacting with water here because I want to say it's producing protons, but I could take that. It does produce hydronium ion in water, right? If I was to add the water, let me write it that way. So if I write it as HCl aqueous plus water liquid, that can react to make chloride minus plus H3O plus. Okay, we're not talking, but those are the same thing in terms of writing them. All right, so that's acids. That's an example of acids. A base. A base, the simplest form of a base forming hydroxide in water is just I would take a base like sodium hydroxide. I put it in the water, and once again, just like up above, it dissociates to make hydroxide ion. And the other thing. It pains me to put the minus here as opposed to there, but I'm gonna do it, okay? Because the minus is on the OH. But okay, so that's the simplest form of a base, but you can have things like ammonia is the poster child for something that actually is going to make hydroxide in water that doesn't have hydroxide to begin with. If I think about putting ammonia, which is a base, into water, and I'm going to do these, your book likes to do these organic chemistry arrows. This is arrows you'll use in organic chemistry. And I'm going to go ahead and do them so you can just see them, all right? We're not doing organic chemistry. You will not be responsible for drawing that. But what that's going to make for us, that's aqueous. I'm having problems with Q's today. Plus, I took an H off of the water, and so what I'll be left with is hydroxide ion. Now I'll draw the negative charge there, since I'm drawing out a Lewis dot structure. That would be a liquid. All right, you guys okay with that? It's the Arrhenius definition. So if we're in water, acids produce H+, bases produce OH-. So let me go ahead and just highlight this in our notes. These are bases, okay, and this HCl is an acids. Okay, yes?
Are they not like equilibrium reactions?
This one we could express. The question is, aren't they equilibrium reactions? Well, you can put 60 molar, I'm going to go, I don't actually know what the KB is for this reaction, so I can't be sure there. All the other ones are pretty much not. So in chemistry, what we do is if something is very, very heavy on the right, in other words, we've got a reaction that almost goes to completion, we will go ahead and draw one of these arrows. And then if it's something that it doesn't go much to completion, or we've got 1% or more of something on one side, then we'll do our equilibrium arrows. Okay, so that's kind of the convention we're going to use for that.
Can be, it just depends on the chemical.
It depends on what's going on, right? And I don't know for sure about ammonia, but we talk about, we said that you could put up to 60 molar ammonia into water. Do you remember that you maybe remember that from previous in the course. It was a constant on the board. You don't remember it. I thought it was cool, but so I remember it. But if you could put 60 molar ammonia into water, and so it's existing like this. Actually, I forgot a charge for you there. Okay, it exists like this in water and not like that. That's a gas, actually. I wrote it as aqueous, but if it's in water, it is. Okay, let's go ahead. Other questions? Okay, you should absolutely ask questions if you have them. Here we got a table of common acids and bases. If you were in somebody else's class last term, they might have made you already know the names of some of these. If you're in my class, I didn't. Now I'm going to. I don't need you to memorize the whole table, but there's some that are important here. First off, we have hydrofluoric acid. This is the really dangerous one that you should be really scared of. If anybody ever talks about hydrofluoric acid, this dissolves glass. It goes straight through your skin and dissolves your bones. Okay, if you work with this, they make you have an antidote right next door to throw right next to you that you can throw on your arm or wherever you happen to splash it. Hopefully not your face. Hopefully not splashed at all. But this is super dangerous stuff. So I need you to recognize that. Hydrochloric acid is the acid that's in your stomach. that helps dissolve things. Okay, it helps you eat protein, it helps unfold the protein so it's accessible to things. And then hydrobromic acid and hydroiodic acid, all of these are strong acids. Okay, and they're super easy to name once you know how to name hydrofluoric acid or hydrochloric acid. You should be able to name hydrobromic acid and hydroiodic acid, right? Same naming convention. So those are easy once you've got that. Then we have sulfuric acid, which is a strong acid that you'll encounter in life. It is the acid is in the battery of your car. Okay, so the battery that starts your car is a lead sulfuric acid battery. It can be charged over and over again, charged and used, and it has lead and sulfuric acid in it. Okay, sulfuric acid gets used in lots of other things as well. And then finally, nitric acid is another common acid that you'll see and use. And there's acetic acid at the bottom. I'm just going to leave it off for now. Okay, I may regret it. Yes.
Is sulfuric the one that's only strong for its first protonation?
Yes, and I'll talk about that.
I couldn't remember if it was that or phosphoric.
So these are all, actually, let me not do it like that. The ones I've given you, they're all strong acids. And I don't, off the top of my head, I don't think any of them are otherwise. For the bases, you should be able to name those. Those are pretty easy, right? The bases are, it's a hydroxide ion. You need to remember what hydroxide is, and then you should be able to name ionic compounds. So lithium hydroxide, sodium hydroxide, potassium hydroxide, magnesium hydroxide, etc. These right here are going to be strong bases. We'll talk about what that means chemically. Okay, but strong means dangerous. Okay. So if you see these, you should be really careful. Oh, let me rephrase that. These are strong bases. Okay? And these are weak bases. They don't really dissolve much in water. These dissolve a lot in water. So you should be really careful if you ever see these. These, magnesium hydroxide, if you've ever had milk of magnesia, hopefully you've heard of it. Maybe you have or not. It's something you take if you have indigestion due to extra acid in your stomach. And so you take magnesium hydroxide and it reacts with the acid and it neutralizes it. It's like a milky colored stuff because it's solid. So it's solids kind of in a solution. So it's an antacid. Okay. Questions? So know the names of those acids and the bases that you need to name. You should just be able to name them. Let's then go ahead and talk about polyprotic acid. So sulfuric acid is an example of a polyprotic acid. When we look at these, let me just show you first off. Let's talk about acidic protons. So we have H2SO4. Okay. Notice that the H's went out front, right? We've seen other compounds, like let's say we do gasoline. The main component in gasoline is C8, it's octane, C8H18. Note that the H's go after the carbon there, okay? However, sometimes you will see something like this. This is acetic acid. This is the acid that's in vinegar. If you see COOH, that H at the end, if it goes COOH, that H is acidic, it can come off. This H's in the front are acidic, they can come off. H's right after a C don't come off. Does that make sense? Those are they're covalently bound strongly. So what we would say is we could call these acidic protons. Acidic protons. Questions so far? All right, so we have, right here we have sulfuric acid. It has 2 protons in front. Both of them don't come off with the same affinity. So a way of thinking about that is I've got my H2SO4. Let's say it's in water. It's going to react with water. And it's going to make HSO4. I took an H plus off, so this is now going to be minus. I took a plus away. Plus H3O plus. I gave water an extra proton. Okay? So it's that stuff we saw before with the arrows. I'm not doing the arrows here. Now, this H is here. What's the charge on an H? These protons? The charge on an H that's neutral is neutral, but when we talk about it as a proton, as an H that can come off, it would come off as a what? A plus. Okay? Well, what's here? A minus. So pluses are attracted to minus, so you might expect that it'd be harder to take the second one off. Okay? So when I draw this, I drew that as an arrow. A single arrow, because this is pretty much 100% going to go to this. Okay? There's some small fraction it doesn't, but it's a small fraction, less than 1%. All right, and then I have my HSO4 minus, and that can react with another water, a different water, and that can make us SO4 2 minus. That'll be aqueous plus another H3O plus. Okay, and I need to go back and change that arrow to make it an equilibrium arrow. Because if we look up here, this side here, we've got, this is going to be almost 100% of the dissociated acid, if the acid having given that first proton, the sulfuric acid given that first proton to water. And then over here, we'd have, approximately 0%. It's some small little bit, okay, less than 1%. But then down here, we're going to end up with mostly this and not very much products. Okay, I'm not going to give you actual percentages because I didn't look up the equilibrium constant for this ahead of time. But it's something, this is some 4%, 2%, 1% over here, and then the rest, 95% plus over here, if that makes sense, in terms of the equilibrium concentrations. Yes?
So is that true of all polymeric acids?
That it becomes harder to take. So the question is that true of all polyprotic acids? And what I'm taking as the question is that it gets successively harder to take more protons off. Is that what you're asking?
No, I was just more or less going to ask, like, if after the first protonation, it's equilibrium after that.
Yes,
Okay.
I'm gonna say yes. There may be some exception out there, but I don't know what it is. I'm thinking of a couple in my head right now. Okay. Yes, Priscilla.
HSO first, is that also a type of acid? Or just the equivalent?
Is this an acid here?
No, the product, HSO4 minus. Would that
Is this an acid? This can't be an acid, and why would that be?
I'm talking about the one, HSO.
This one.
Yeah.
That is an acid.
Okay.
Yes. So we're treating it as an acid here. It is donating, well, I haven't talked about the Bronston-Lowry definition yet, but it's going to give up an H plus. Okay. Let's go ahead. Let's do one more thing, and then we'll talk about this proton donor and proton acceptor is the next definition we're going to use, which would be useful to talk to you about now, but I haven't used it yet. So before we do that, though, let's go ahead and look. We've got two reactions here for our polyprotic acid. Go ahead and add them up. Add them together and can't combine terms where we have combined terms and cancel terms where we cancel terms. Let's get the overall reaction of both of those going together. Okay. I'm gonna do this the long way. I think in the past, sometimes I've gone and canceled before I pulled things down. I would pull everything down in my adding up and then I'll combine my terms. So what I'm doing here is H2SO4. I'm not gonna bother with my, states. I've got a liquid water, so I'm pulling off the top reaction. I just pulled my two reactants. Excuse me, off the bottom reaction, I'm gonna pull my two reactants. Okay. Then I've got something going on. Second one's an equilibrium, so I'm going to make this an equilibrium. And then up the top, I'm going to pull both my products. And on the bottom, I'm going to pull both my products. All right. We do this in chemistry, and so if I had equilibrium constants here, I'm adding them together, so I would multiply my equilibrium constants together. Okay, we don't have them. But last chapter, we learned that when we add two things together, we multiply. Does anybody see any terms I can combine or cancel? What do you see, Priscilla?
The H2O could come together and then 2H2O.
Yeah, so I have 2H2O, right? Did you say H3O?
Oh no, I
Okay.
meant H2O, and then the H2O could cancel.
And then I think you're seeing the H2, the HSO4 and the HSO4, those cancel. Okay. And then one more thing to combine.
H2O.
Yeah, these H3Os. So over here on the other side of the reaction, I have 2H3O plus. Okay? And then what I'm left with is I have H2SO4 on this side, and on the other side, I've got SO4. We already took care of these. SO4 2 minus. That needs to be a 2 minus. This may have locked up. Will it lock up for that? Give me a minute.